Bill's introduction for me. I'm the outreach coordinator in physics and astronomy. We do astronomy too, so keep us in mind for your astronomy lessons as well.
My problem is I've been around Purdue long enough that it was physics, so I'm I got to keep remembering and astronomy. So sorry, David.
Changed a few years ago.
Yeah.
So we're going to present 2 lessons to you today. One is called Ramp and Roll. The other one is called Newton's Cart. And excuse me, these are both lessons that were actually created by Zeynep Akdemir. Zeynep is a graduate student in curriculum and instruction here at Purdue, and she's currently in Turkey. We've worked together all summer to put these things together for you. So with that, I'm going to pass it over to Zeynep and let her go ahead and get into the Ramp and Roll experiment, and then I'll take the reins back and talk about Newton's Cart, and then we'll combine forces in the end. So, Bill, did you have a comment?
Yeah, I did. If you have questions, go ahead and put them in chat, and then I'll type in and ask them if it's in the middle of something. David, Zeynep, are you going to be presenting something? Or are you going to actually take over the screen?
Yes.
I have PowerPoint slides, so I think you co-hosted me, so I'll be able to share my screen too.
See if you can share. We had an issue yesterday of not being able to share as a co-host, and I can move it for you if we need to.
Do you want me to try now?
Yes, please.
Mm-hmm. I think it worked.
Okay, I think it did too. Great.
Okay.
Zeynep, why don't
thank you so much.
Zeynep, you go ahead and take it from here, and we'll follow along.
Sure. Thank you so much. It was great to work with you this summer, Dr. Cederberg. So, and welcome you all. My name is Zeynep Gonca Akdemir from Turkey. I am a third-year graduate student at the Department of Curriculum and Instruction in Science Education. I just start with a little bit about me. I am originally from Istanbul. Right now for summer break, I'm in Istanbul, but we have been working with Dr. Cederberg about this lesson plan to meet with you.
Zeynep, I'm going to pause you for just a minute. Would you go to presentation mode on your screen so that you're full screen on your PowerPoint?
Sure. Mm-hmm.
No, I think we lost the image. Okay, I think we're back.
Can you see my full screen now?
Yes. Yeah, that's perfect. Thank you.
Yeah. I am a graduate student, PhD student in the Department of Science Education, and my current interests are looking at student sense-making skills and how teachers actually contribute student sense-making skills by looking at their behavioral, emotional, cognitive, and social engagement skills. So this is my recent current research interest, and in the lesson plans we have been creating, we mostly paid attention to creating some different assessment questions, which were specifically looking at student sense-making skills and how teachers can contribute that too. So along that line, I'm trying to, so in the lesson plans, we wanted to highlight Newton's laws of motion, and the rationale for our lesson plans and for those 2 experimental lessons, first of all, was correcting students' misconceptions about force, motion, and energy. Before creating the lesson plans, we did some literature review about certain potential misconceptions that middle school students can have. And we wanted students to make sense of the elements of Newton's law by experiential learning. We didn't want to have their minds on experiences. Also, we want them to have hands-on experiences too. And of course, we want to provide you some sample lesson plans that you can revise and also use as it is in your future lessons. So when we looked at the literature, we came across certain misconceptions starting from elementary grades to the higher education, actually. And I tried to highlight some of the misconceptions we came across. For example, motion implies force, or no motion implies no force was one of the common ones we encountered. Rocket propulsion is due to exhaust gases pushing on something behind the rocket. Actually, this was one of the driving, guiding element that guiding a misconception before we created the Newton's card lesson plan. Also, constant velocity means no force acting on the object was one of the misconceptions when differentiating force versus velocity. Faster moving objects have larger force acting on them. Heavier objects fall faster than lighter ones. Large objects exert a greater force than small objects. Force is energy was another interesting misconception we encountered in the literature. Gravity increases with height. Force must happen when two or more objects contact with each other. And also for the acceleration versus other elements, some misconceptions were about the maximum acceleration, which is maximum velocity. Larger velocity means larger acceleration, and same velocity means same acceleration for two objects. We can share those resources with you if you are like specifically interested later on too. I just wanted to highlight some of those to take more attention in that part. So when we looked at the elements of the Newton's law, we mostly give importance of the second and the third law, which were like building the relation between mass and acceleration. And the third one, as all of us know, action and reaction forces we wanted to give more attention to. And we kind of like selected those concepts based on the next generation science standards, even if Indiana has not like built it essentially yet, but we kind of like got our framework from this standards. So for the Newton's, actually I can stop sharing my screen here because I would like to first of all mention about the Newton's card experiment we have. Dr. Cederberg, would you like to give some like material introduction, or should I like start talking about the materials I have in hand? So would you mind if I start with that, or?
Why don't you go ahead and do that? Sure. We can talk about the materials for both experiments. If you want to start with the ramp and roll, I can show the materials. Let's start with ramp and roll. I'll show the materials that the teachers were sent and provided, and then I can talk about the Newton's cart model when I get to that part. How's that?
Okay, thank you so much. I was just confused. Okay, I'm sharing my screen again then, thank you. So for the ramp and roll experiment, our focus was more on Newton's second law of motion. So we wanted students to understand the relationship between mass and acceleration and how it creates the force. We also wanted them to understand gravitational potential energy, kinetic energy, and law of the conservation of energy. So that in this lesson plan, we actually divided the lesson into two parts. I would like to share a video here. So just to I will be able to share the video like that. So let me stop Let me stop sharing my screen so I will be able to share it. Let me explain it from here. Actually, I was not able to share it. So in the video, I was about to show you the exact like episode that we gave you in the YouTube video. First of all, we want students to release the marbles from the top of the incline ramp. So we had 2 ramps. I actually tried the experiment with 2 ramps. One of them was 75 centimeter long. One of them was 50 centimeter long. And we had 2 different ramps like that. And we wanted to use one marble and release it from the top of the inclined ramp, just to make sure that they are released from the same height, so that they are released from the same place but from the different heights to do the experimentation. So I would like to share you the video, but I have some technical problems. I'm so sorry for that. So I'm unable to share the video with you, but let me continue with the sections of the lesson plan. So we had 2 different parts in the lesson plan. One of the first part was asking students to understand distance, time, and velocity relation. So we actually want them to get the idea of velocity. But here it was important for them to understand that when the marble reaches the bottom point of the inclined ramp, they will be able to calculate the average velocity. So here the distance traveled and the time of the travel changes, and we kind of wanted them to understand this difference. Here you can see how we ask them to gather the data. So I provided a picture on the left, which is built with the 5 centimeter high inclined ramp. This ramp was 50 centimeter long, and the ramp on the floor was 75 centimeter long. And we wanted them to experiment how far the marble goes when the height changes. So as you can see, I created the data I have, and as you can see, I'm sorry. Are you able to see the screen properly?
Yes. Yeah, we can.
So we wanted them to also understand the concept of a unit conversion here. So I created the data for you just to show that as the height increases, students will be able to see that the distance travel increase and the time also changes. So this is just for them to understand that as the gravitational potential energy increases, their kinetic energy increases. But here we just want them to see the distance difference. But for the second part, we want them to make sense of the concept of average velocity, because they start to measure the distance when the marble reaches the bottom point, and they record the time accordingly so that they can get the velocity. If this part is clear, I want to explain how we want them to graph the data they have. So we actually showed them a blank data sheet and want them to record the data of the time and the distance, just to see that as the height increases, the distance also increases based on the energy change. But in the second part, experiment B, they will be able to understand the transformation of energy. So the second part was talking about the energy transformation and energy conservation. And here you can see the related NGSS standards also. They were all available. So for gravitational potential energy, I would like to show from here that for the gravitational potential energy, we we actually in the student shift sheet gave them the formula, but before the formula, they should be able to understand the entities in the formula because gravitational potential energy depends on the height, so they should understand the importance of height in the formula first. So we don't want them to memorize the formula. We want them to understand that the gravitational potential energy turns to the kinetic energy as the marble travels in the track. So for the kinetic energy, they do the same, but based on the first part of the experiment, they can use their data for the 5 centimeter high track so that they can create their own energy solutions here. And we want also them to understand that the sum of the initial energies should equal to the sum of the final energies. So they should be able to explain the initial energy in the system, also final energy in the system. So this experiment actually will show them how the results also align based on the data they have, and they will be able to do different trials as scientists do in the real life. And at the end of the lesson plan, they will be able to compare the initial and the final energy. If they cannot find the aligned results, they can also do extra elaborations like the effect of friction force or the effects of air friction or something like that, that they can just do brainstorming on that. And the important part that we want to kind of like drive here was the making sense questions. Actually, we wonder how you teachers actually can elaborate on this. So I wonder how you think about those two. So let me check my last slide. So and as an additional idea, in the YouTube video, we also try to mention that you can use in your lessons like marbles with different masses. You can ask your students to try this as different variables. Also in my setting, I was able to use a soft floor and friction applied in my experimentation process, but you may ask students to try hard floor too, and different ramp material would kind of differently affect your results too. So let me stop sharing my screen. My presentation is that. So please let us know if you have any questions or any like ideas in mind.
So there was a question. There was a question that was asked. They said that the misconception chart that you have was very organized. Do you have this for all teaching categories in science, or do you know where to get that?
I actually did a literature review for that. This chart is specifically for force, motion, and acceleration, but definitely we can do our best to like create charts for different lessons too. But for now, I have a detailed chart for this these lesson plans only.
So the answer is they're not just out there. You have to go out and do a search and pull it together, correct?
Yes, for this we just have.
I responded to the comment and said we would put these resources in the drive folder for this lesson.
Okay, David.
Yeah, I'm not sure I have a connection. Can you hear me?
Yeah, you're kind of cutting in and out.
Okay. Our connection is a little sort of moving. So I will say that I will put folder for this lesson.
We may share the articles also, Dr. Cederberg, if you'd like. So we can create a folder with the articles so they can access that.
Yeah, we'll just take the articles and put them in the Google Drive. We can do that after. Somebody also asked for my email. Put that in the chat as well. Am I coming through okay? Can you hear me?
You're cutting out pretty bad.
Okay, I'm going to log out and reach.
Okay, log out, come back in.
If there is any question about the ramp and roll lesson plan, I can take the questions until they came back. So, or have you had the chance to do the experimentation on your own? Had any troubles or something?
I don't have any trouble with it, but I like to do ramps and marbles with my students. And another thing that we've done, because especially like 6th, 7th grade, they have a hard time understanding acceleration. And so it takes some doing and a lot of trial and error. But what we've done on our ramps is to keep the ramp pretty low so it doesn't go down too fast. But when they release the marble, they have somebody spot where the marble is every second down the ramp. And they put a marker there, and then they can see the distance getting shorter and shorter between each second. And then we can also do some accelerate, like that change in velocity. Okay, between the first second was at this velocity. By the second it was at this velocity. And they can visually see those marks get closer and closer together. And so that seems to have helped them with the idea of acceleration too.
Have you had the chance to look at the making sense questions, also sense making questions? I really wonder, because of my research, like how you would revise those questions or you would apply that in your classes. Seems like everything was clear, so. There is one comment, but. There is one question. Is there any text on Newton's law that would work well for students to read along with this hands-on experiment? Actually, I used different materials from different websites. I did not use the settled text, but like any textbook that you use at your school would work, I guess. I just used like different resources for the lesson plan we created. So I hope I was able to answer your question, but.
David, could you unmute and see if you are back on?
Yeah, can you hear me now?
Yes.
Okay, sorry, the connection here is terrible. I changed locations. So I think I have what I need, but we're doing okay. Can I go ahead and continue?
Yeah, go ahead.
Let me know if I have connection issues. I wanted to take a minute to show the folks who are wondering the materials we used, the ramp and roll. At Bill's suggestion, we were trying to figure out what kind of track works best. At Bill's suggestion, we went out to one of the local box stores and picked up some corner guard that is rounded.
David, David.
I was surprised that balanced. Yeah.
I don't know about everybody else, but you're cutting out for me big time. Andy, is he cutting out for you? Okay, good. Yeah. Your video's gone and you're cutting out.
Okay. Let me go to a different room real quick.
I'm sure none of these teachers had any of these issues during COVID, right? Yeah, no, right? None. Yeah. Everything works great every time. Mm-hmm.
While he's relocating, I'll come off of mute and ask a question.
Okay.
I was not, so, I'm sure I'm not the only one, even though I've gone through these physics classes as a college student and I've been teaching it for a while. Sometimes you just feel a little insecure when you're teaching it, especially us middle school teachers that are jack of all trades, but sometimes masters of none. And so I like this lesson because I think it's very layered and it's an opportunity to teach a lot of these really complex ideas, but all bringing it back to the same topic or the same experience, which I think is really neat. But I didn't see a lot of the answers and things in the teacher resources. And even though I did the activity myself, I just kind of wanted that reassurance that I was getting the results that I was supposed to get or intended to get. And then the other kind of comment that I had in doing it is I think the activity is great, but I think some of the math logic would be a challenge for my 7th and 8th grade students. I'm located in Ohio. So in Ohio, this would actually be our 8th grade standard. And I think some of the math could be a little bit of a challenge, but if we worked on it together, I think we could all get there. I think we would just have to help them interpret the math instead of them coming up with their own interpretations very easily. Sorry, I'm long-winded.
No, you're fine. And I'll pipe in here. So you guys don't know me that well yet, but I taught middle school for quite a few years and actually taught 8th grade and did this exact lab in 8th grade. I don't know if your kids rotate from, we were on a team of, English, math, science, and social studies. So that the same kids that I had the same math teacher. So we worked together on this so that we could use the data then to go in and analyze and use further in a math class. It was great because then when I was doing it in my class, the kids were understanding better. So if you can somehow work with your math teacher as well to go through this, one, it helps with some common terms that you should be having with each other. So I think that's pretty important.
May I add also some point? Thank you so much for your comment. For the key part, actually, we thought about this, but we didn't want to include the key because since every time when we do the experiment, we will be able to access different data. So the data you have can be different from mine and other teachers too. So for the key part, I was not sure to add this, but definitely we can do our best by working collaboratively to add the ideal key. I don't know how Dr. Cederberg think of that, but I think that could be the best solution for this.
I think I've rejoined the group. Bill, Zeynep, can you hear me?
Yes, now you sound a lot better.
Okay, so I'm disoriented. I'm out of the room where I have all my stuff, but this is teaching, right? I don't know where you are in your conversation. Am I okay to go ahead and get into Newton's cart?
Yes, I believe you can go ahead and start that.
Okay. I caught bits and pieces of some really good comments about the ramp and roll. And somebody commented that maybe shallower angles are better than higher, larger angles. And we did find that to be true. It's much better for students trying to do timing. Excuse me. I'm going to share my screen. Okay, am I good to go? Okay, we probably used a little more time than we needed to here, but I will get into the Newton's cart experiment. I just want to say kudos to Zeynep, who created these two lessons, and it was a pleasure working with her. She came to me because of a course I teach, Physics 595. It's a graduate level course in instructional design and physical science. I mention this because if any of you are interested in graduate credit, you can take this course remotely. If you're interested, contact me. We can figure out a plan. There is, if you're in Indiana, there has been funding available through the Hoosier STEM Academy. So that's an option if you would like to think about that. The good thing about Newton's cart is it's a great visual for the third law. When you talk about rockets, action, reaction, where the forces are acting, in what direction they're acting, all of these things build into both of these lessons. With Newton's cart, we can actually look at the initial and final velocities. We can calculate the average velocity, and I will show you how to do that. I think I'll skip and go on. If it may be outside your grade level, but we can also do momentum and acceleration with this experiment. Lots of variables to control. I'd like to get some feedback, and I say, you go first. Who has tried this? Who can tell me if they tried it and how it went? I'd like to have your first impressions. Who's got one? You can unmute yourself and speak up. Who did it? Tell me how it went.
I thought it was a little challenging just at first to get everything kind of set up. But once I got it going, I thought it was really cool. And I was like, oh, this is a pretty cheap experiment for the kids to see. And it'd be something easily that I could recreate in my classroom.
Thank you. I think it's a terrific experiment. I would say that it's probably an experiment in progress. I love the design. I love the potential that we can do with it. I will also acknowledge that I think if we supplied you materials, the marbles, the steel and glass marbles that we sent to you probably work fine with ramp and roll. They're probably too small for Newton's cart. And I found that if you use a steel bearing, something in the area of maybe 5/8 of an inch or 3/4 of an inch might be a little better. Well, is a little better for a couple reasons. Number one, the larger marble has enough more inertia that the cart recoils further, and that's an advantage. And we'll talk about that in a couple minutes. Anybody else have a quick comment?
I had a hard time when I was cutting this string, getting my scissors were getting in the way of the motion.
Me too. So I played around with this. I collected data over on and off over the better part of a week. and came to the conclusion that the scissors I had were a problem. And I will talk about that. So in fact, excuse me, I'm going to break out here and show you a couple of videos that that I recorded of some of my experiments. So I'm not, there we go. This was one of my first trials, and I just wanted to set it up and see how it worked. So this will be a slow-mo video, but watch the scissors relative to the cart. That was a pretty clean cut. And that gave me enough distance with the cart that I could measure it. The problem for me was I was doing this alone, and this is a group activity. I can't run 2 stopwatches at the same time. So that was a challenge. Here's another example. Again, keep your eye on the scissors and the cart. That was a cleaner cut. I got good distance from with the ball and recoil of the cart. And both give me good opportunity to measure both time and distance. When your cart only moves 20 centimeters, it's kind of a short time span, and it's difficult to measure. Now, sorry, noise in the hallway. I'm going to show you one more example. We get better as we go along, and I discovered new things. Now, in this example, my scissors were definitely a problem. So we wrote the experiment using a string. And I'm going to stop sharing my screen here for a minute. So we used a string, and the string might be easier to cut in some ways than a rubber band. But now, before I changed rooms, I had a whole bag of rubber bands, and I don't anymore. But if you use a string, you can mark. I tried making marks on the board, like calibration marks. But using a string, it's difficult, and kids are going to have a real problem trying to tie a string to get to the same mark to be able to repeat the experiment. If you're going to do a one trial, fine. But I think little hands have a hard time with tying string. So I resorted to using a second rubber band. So I had one rubber band that would be the firing rubber band, and a second rubber band, which would be the pullback rubber band. The advantage to that is if I have a bag of rubber bands that are all alike, I can repeat the experiment multiple times. So I think that's a good idea. If anybody has anything they want to share, I'd be all ears. But I will say,
like that, I
have
2 rubber bands like that, so I can show it for them. So I tied 2 rubber bands together, so it will be look like this. So can you see the second? Can you see the second rubber band? So it's here. So if you use a shorter one, it's gonna have more tension, so we'll be creating more potential energy here.
And that's cool, because if you have pieces of rubber bands, so buying rubber bands, I realize they come in different sizes. There's number 33, and they're different diameters and different thicknesses. Try different sizes, try different diameters, try different thicknesses. And the thing I think that is the secret to making this work in your classroom is finding what works for you. That would be, in fact, I probably have, I'm going to go back to my PowerPoint here. And
Hey, David,
yeah,
there's been they're having a discussion on the chat about two things. One, having the marbles go everywhere, how can you keep them kind of contained as they shoot out? And there's been some talk about whether, you put meter sticks or something on each side to stop the balls from rolling everywhere. And then the other one was talking about twisting the rubber band to make it shorter. That way you could change that variable with regards to where you start, like you were trying to replicate each one. So you could twist the rubber band to make that happen as well.
That's a great idea. Twisting the rubber band would make it shorter, giving it less stretchability and more force. That's a good idea. It also might be easier to cut the rubber band if it's twisted. So I think that's a great idea. In fact, I was sharing this experiment last night and watching the videos that I shot with one of my grad students. And the first thing he said to me, because I was holding the scissors this like sideways and cutting, and the first thing he said to me was, "Why don't you come down from the top? It'll be a whole lot easier." And it's like, I never thought of that. We kind of just go our way, and it's nice to have other options. So I do think typical scissors are probably difficult. So I would recommend some tighter, sharper scissors. It may be more of a hazard for your students, but they may work better. And I think we can trust them with scalpels. We can trust them with sharper scissors. I'm going to go back and share here. So I think we've talked about some of these things already. How to keep the balls in line so that they don't go all over the place. That's a challenge. Sure, you could use meter sticks. Pool noodles might work well. I've taken pool noodles and even cut them in half. There are various things you could use. Rope, just get some lengths of rope and lay the rope, create the tracks with rope, tie them down at one end, at both ends, I'm sorry. And you have a foot wide path, and the marble can go in that path, and it might hit either side, but at least they won't be going all over the place. And adjust the mass of the marble, strength of the rubber band, and get the marbles to go at a distance that's convenient for you. So we did, the student handout has some calculations that we guide the students through. We can calculate the average velocity. I think it's cool to calculate the launch velocity. So if we know the average, the initial velocity, and we'll call it the launch velocity. If we know the initial and final, we add them together, divide by 2, we get the average. Well, the final velocity is 0, because if you let the ball go all the way to the stop, then final velocity is 0. So you can actually calculate the launch velocity. I have some other recordings, but you don't need to see them. I don't want to take the time. Students can have practice in collecting data. They can have practice in calculation of the variable quantities. They can have practice in graphing. So there are a variety of things that students can do to graph their data. And maybe that's not important for you. Maybe just calculating the initial velocity is fine. But if you want to get into some graphing, here are some options that students could do. And if you have any other ideas, again, I would be happy to hear them. Bill, are there any other comments or questions?
I mean, the comments that they're, they would be great for older students for scientific design. They're looking at a lot of variables, which is true. There's a lot of variables you could adjust in this, which is great.
I think there's a lot of flexibility in this lesson. We kept it fairly simple this time around, but I have talked to a couple of high school teachers who are excited about doing this in their AP class because they want to get into acceleration and momentum and some more complicated things, and that's great. I think that's possible. If you want to, I mean, you can calculate acceleration, you can calculate force. Both those things are possible, and with the simple measurements that we are collecting, you have the information to do that. Now, I'm going to break out of the PowerPoint, and I want to go to an Excel sheet. So here is some data that that I collected. I'm going to, is that, Bill, is that legible? Can you see that okay?
Yes, I can see it.
Okay, it might be a little small. I just wanted to, and I will put this or a version of this in the drive so that you can copy my ideas and copy how I did this or come up with a better way. So I wanted to keep track of, number one, the mass of the ball. So the ball that I did this with was a little bigger than what I had before. It was about 5/8 of an inch, 11/16. Its mass is 21.7. I have the mass of the cart, 57 grams. So I used two rubber bands here, the firing rubber band and the holding rubber band. They were both the same size. They were both number 32 rubber bands. I have a note here, hole 2. I'll explain that a little later. So here are 5 trials.
Hey, David.
Yeah.
It is 10:50, so you need to kind of wrap up here fairly soon.
Okay. I don't need to go into every detail. You can see this. It'll be in the drive. Distance versus time for the ball, I thought was pretty good. I've got one data point here that's a little awry. The cart distance versus time is not at all good. I'm going to attribute that to the fact that I had big scissors. I might have been, in fact, I did my scissors got in the way of the cart motion. So, with better scissors, I think this will be a little better data. So I calculated the average velocity. I got the initial velocity. And so the formulas to do this are here in the spreadsheet. I will make this available, and you can have access to that. Let's see, is there anything else? No, I think that's the end of my PowerPoint. I'm going to stop sharing here and come back to live. I've got 2 things before I wrap up. First of all, I have a survey that I would like to have you fill out. I just put the link in the chat. The more I can get back from you all, the better we'll be in the future. So I'm asking for your comments on the lesson, particularly how it might be appropriate for you, how it would work in your classroom,